Okay, so this is the top of page 11. We're going to be learning about Avogadro's principle. And if you remember, this Avogadro guy was the guy that had his own number. Avogadro's number was 6.02 times 10 to the 23rd, which we would write as E23. And that number was there to help us count molecules, figure out how many molecules there were of a substance. And he was also the guy that came up with the counting unit of a mole to help us count those molecules. So that's the same guy, and he came up with that number, and he came up with the idea of a mole by studying gases. So this Avogadro's principle is another thing that he discovered during that time. And what he discovered and kind of put down on paper is that equal volumes of gases, even if they are different gases, and you'll notice in these problems we're talking about down below, we're talking about two completely different gases, oxygen and ammonia. But even with different gases, as long as they're at the same temperature and pressure, what he found was that they contain the same number of molecules. So once again, he's all about counting the molecules for our different substances. So he does have this kind of equation credited to him. I'm going to rewrite it. Instead of writing out volume A, I'm going to write V1 just to kind of make it look a little bit more simplified. Ooh, why did I put N2 down there? That's weird. My brain was already on the 2 side of the equation. So this is a little bit more like what we would probably expect to see as an equation here. And this should actually look kind of familiar to you, especially after I switch that to be 1s and 2s. This almost kind of sort of looks like the combined gas law, doesn't it? If I add in my P1, P2s, T1, and T2s. And so this really is just kind of a special situation and application of that combined gas law. If you remember, if something is the same when we're doing a combined gas law problem, if it's not changing, if it says that it's constant, or if it just doesn't mention it at all, then we can leave it out of our equation. So here when Mr. Avogadro was saying that we have the same temperature and pressure for our two gases, that means that temperature and pressure aren't changing, which means they can be left out of our equation. And so this equation isn't anything brand new. It's just a simplification of that combined gas law. And it's being applied to two different gases, two separate gas substances, instead of just taking one substance or one gas sample and changing some of its kind of measurements or quantities. We're taking two completely separate gases and comparing them. But this is telling us, his law is telling us that we can do that. It's basically the same as comparing similar gases. So in this first problem here, you see that we have 5-liter sample of oxygen with 2 times 10 to the 23rd molecules in it. If I have a 5-liter sample of our ammonia at the same temperature and pressure, as long as they're at the same temperature and pressure, if I have the same volume of our gas, that means we're going to have the same number of molecules. So I don't even really need to use a calculator here. I know my answer is going to be 2 times 10 to the 23rd molecules. Now, of course, I would want to see some kind of work or explanation for that. And it's easy enough to just set this up, even if I'm not actually doing any cross-multiplying or dividing. I can see that 5 over that 2 times 10 to the 23rd is equal to 5 over some number. Well, if it's 5 on top both times, then it's going to be that same number on bottom both times. So you can still show some work, even if everything you did was mental math there. So that's just the basics of his law. Even when we have separate substances, completely separate containers, we can still know some things about the molecules in both. Now, 6 isn't the same volume. It's kind of the same container of oxygen. It's a 5-liter container, has that same number of molecules in it. And Now it's saying how many ammonia molecules would be in 10 liters. Well, even though this isn't going to be exactly the same, we can still kind of draw some conclusions about how that volume has changed. My ammonia is in a volume that's twice as big as the oxygen. If it was the same size, it'd be the same number, but if my container is twice as big, then we can probably already figure out, once again, it's going to be twice as many molecules. So my answer over here is 4 times 10 to the 23rd molecules. And I can still show our work here and set this up. It starts off the same. I'm going to use the E here, though, just because it's a little bit neater, easier to write out and set up. So here, when this goes to 10 liters, I can absolutely cross multiply and divide, but that will get me the same answer as if I notice this doubling the top number is going to double the bottom number. Those simple numbers, a straightforward doubling and halving, we're doing that on purpose when we give you problems like this. So we're trying to save you time. We want to see some work there, but if you can work that out in mental math, you can get that answer and be confident in your answer, and then just make sure you're backing it up with a little bit of work. So this next problem is going to be a little bit more involved. It starts off looking a little simpler because we start using the unit mole to count those molecules, so we don't have to deal with that scientific notation. And still here we have doubled our ammonia volume, so that means we're going to be doubling our number of molecules here. And I could even do this math pretty easily. If I was cross multiplying, I'd be doing 5 times n is equal to 20, and then dividing by 5 to get n by itself, and 20 divided by 5 is 4. But I knew that already. Once I knew that 5 liters held 2 moles of oxygen, 10 liters is going to hold 4 moles of whatever substance we're working with. The only problem is after I find that answer and put the units on it, I might notice it wasn't actually wanting to know the number of moles. We were wanting to know the specific exact number of molecules here. So this is like some asking, oh, how many donuts did you get? And you're like, oh, 2.5 dozen. Like, I mean, okay, that kind of answers my question, but if I want to know a number of donuts, just tell me a number of donuts. So here, I want to know the number of molecules, so we're going to need to turn these moles, this counting unit, into the actual number of molecules if that's what it's asking for. And the way we're going to do that is with this 6.02 number that we wrote at the top of the page. Hopefully you did write it up there. You didn't think I was maybe just being nostalgic. If you didn't write it down, I would suggest you write it down just to remind yourself in the future if, say, you have another problem like this someplace, sometime. Yeah, that's all I'm going to say about that. And just remember, since I have moles up here on top, that means that the 1 mole part of my Avogadro's number equation is going on the bottom, and then the 6.02 E23 molecules goes on top. And I'm going to have to make a little bit more space for this answer, but take a moment, maybe even just pause the video here and see if you can put this in your calculator again. Practice doing this in your calculator to see if you can get the same answer that I get, because if you can't, I want to help you get it. Sometimes just getting this E in there or formatted correctly is a struggle, and it's been a while since we had to, so I want to help you get it there. Okay, so if we've done this correctly, then our answer should come out to be 2.408 times 10 to the 24th. And that 2.408, I actually want to round to 3 sig figs. So I'm going to keep the 2.4. I want to keep the 0, but the 8 that's after it is going to round that up to a 1. So that's 2.41 times 10 to the 24th molecules is our final answer here. Now, let's go on to another kind of variation on our gas laws we've already seen. This one, though, instead of being a kind of special case or variation of our combined gas law, this one is a variation or a special case of our ideal gas law. So here, I can just imagine Mr. Avogadro doing all these equations and calculations with gases and calculating number of moles of gas, and making sure everything is perfectly standardized so that everything is perfect. And so he's doing all of these calculations at our standard temperature and pressure, and over again, he's plugging in the same number for that standard temperature, the same number for that standard pressure. And if you watched our podcast over this equation, you'll know that R is a constant as well. So if he's being consistent in his measurement, that R is going to be the same number as well. And these were the only parts that were really changing in any of his calculations, was the volume and the moles. And those were the only things he really cared about, like what we saw in that equation above, just volume and moles over and over again. So what he decided was, well, if I've standardized everything else, instead of plugging all of these numbers in over and over again, let's just standardize this volume as well. So what he did is he plugged in 1 mole for N, and he calculated what volume that gas should take up. Every gas, in fact, should take up. As long as we're at our standard temperature and pressure, 1 mole of any gas should take up 22.4 liters, as long as it's acting like an ideal gas, following all of those rules that we learned about in that first podcast. So that's all that we really did here. And we don't really need to have this equation written out. All we really need to remember is that if we're at STP, then this conversion, this equation here, is a shortcut that can get us straight from moles to liters or back again in a single step, a single calculation, instead of having to plug in 4 numbers, rearrange an equation, and hope that everything goes right in our calculator. It's a lot shorter and simpler. So let's go ahead and work out a couple of these, because it is just a little bit more dimensional analysis. I have this 135 liters of oxygen, and if I use this equation, if liters are on top, then that means I need to put the 22.4 liters of oxygen on bottom. 1 mole goes on top of oxygen. And so I'm just having to do 135 divided by 22.4, and that will get me my actual answer. And this turns out to be 6.028, I think. 6.026, which would round up to 6.03 moles. Much simpler, just 2 numbers to put in the calculator, no debate about how to rearrange them or organize them, just do top divided by bottom, done. Now, you'll notice I almost forgot my substance in my answer, and I honestly almost didn't put my substances in these spaces here either. They're not required for this specific question, because the only substance we're working with in this entire question, the only thing it mentions, is oxygen. In those stoichiometry problems, we had to have that substance written down because every single problem had a chemical reaction that had multiple substances in it, and every question even was giving you one substance and asking about another. So you had to specify what substance you were working with because there were so many options in those problems. But here, there really aren't. So on the rest of these problems, I'm probably going to leave out that substance just to keep it simple and to focus on the numbers that we've got, how to work with them with the units and how to organize those. If you write the substance in there, just make sure that it's consistent all the way across. We shouldn't have different substances changing in these problems. Now, some of you might not really like dimensional analysis that much, and you might think that it would be easier to plug in our standard temperature and pressure. If you know what those are, you could go and find your temperature and your pressure. Back from page 3, you could plug this 135 in as your volume, choose an R value, and you could still calculate for moles by doing PV divided by RT. That works. It does. This is just a shortcut. So some of these problems you're going to have a choice. When I see your work on the quiz, some of you might have worked it out one way, some of you might work it out another. Just make sure you remember that we can only use this shortcut if we're at STP, because that's the numbers that we plugged into that temperature and that pressure to get this 22.4 number out. So the real power when I really will use this every single time is whenever grams are involved in these ideal gas law problems, in these problems where we just need a little more information. Because grams, as soon as I see it, sure, it wants grams, but I know I'm going to have to figure out what my moles are first from my equation, because grams aren't in any equations. So I'll have to use my equation to find moles. Then I'm going to have to do dimensional analysis to turn those moles into grams anyway. So if I already know I'm going to have to do a little bit of dimensional analysis later, I could start this same process, 35 liters, turning those liters into moles, just like what we did in the last problem, just because our diagonal is the same with those liters. And then I just need to keep going a little bit farther. Nitrogen, if we check the periodic table, is 28.014 grams per mole. And the 1 mole part of that needs to come down onto the bottom because I have my moles on top here. And then the 28.014 grams will fill in the top. So this is all we need to do here for this problem. I think in our podcast on page 9, I had an example that involved grams, and you had to plug the numbers in, solve for this, stop, remember that wasn't your final answer, and take it and do some more calculations with it. And anything that you do in multiple parts and multiple calculations is just more complicated. At its base, it can't help but be more complicated. So this answer does turn out to be 44 grams. Keeping 2 sig figs because that's what we were given over here. And I really think that this is the easier way to work out this problem, for sure. This next one is back to being simple. I asked students in class to work this one out themselves, but I'm just going to kind of set this up here. It's kind of set up the same way as the other ones. Your calculator might be telling you the answer is 0.5. This is one of the weird problems where technically we need to add a couple more sig figs because our given had 3 sig figs in it, but still basically the same process as the first question. Now, let's look at the last question because once again, it has grams in it. And so it's going to be one of the ones that's definitely going to benefit from this shortcut, from this process. This one, though, starts you off with grams of ammonia. And I didn't have to write the ammonia here, but this is going to give you real stoichiometry flashbacks probably, because this is something we could have started with in stoichiometry. And anytime, and we did several times, we have grams of ammonia on top. We're going to put grams of ammonia on the bottom, 1 mole over it. Still the same basic process. Anytime you start with grams, cancel them out, turn them into moles. Now sure, I could stop, calculate, find this answer, use that as my N when I'm trying to find my V, and plug that into my PV equals nRT to find my V, but I can also just go one more step using that equation at the top, just making sure the 1 mole part of it is now on the bottom because my moles were on top before, and now the 22.4 liters goes on top. And this is going to get us to our volume, our answer, a lot quicker than having to do it the long way with all of that other algebra stuff. So I would heavily recommend that you use this method anytime you have an ideal gas law situation at STP, but especially if you have grams involved in an ideal gas law problem at STP. But remember, it does have to be at STP. It's the only time that this shortcut works, but it helps. Now, while you won't find any problems that are at STP on page 10, of your packet, you will see at least one on page 12 where we have the mixed up review problems for our quiz. So maybe flip to page 12 and see if you can find one of these problems to try out.